Okay, 5 minutes past. I think I will start. I suspect quite a few students will not show up today because what I have to say, at least for the rest of the lectures, would be familiar to those students who have taken relativity. Right? It's really a synopsis of what was taught in that course. But from this point of view, if you have already learned basic formulas for connections, for curvature, it's actually relatively simple. And I just give a sketch, I mean, so that to enable you to read up the literature with a particular perspective. Okay. So let's start with a very quick sketch of relativity in general relativity in 30 minutes or 1 hour. Okay. Well, general relativity, as you know, is just a theory of gravity that replaces the Newtonian inverse square law. And in many ways, in terms of its formalism, it's similar to electromagnetism. In electromagnetism, there are really classical electromagnetism. There are two parts to the theory. Classical magnetism consists, first of all, of the Lorentz Force Law, which tells you how the charged particles move if the fields are given. All right, so if you give me E and B, then the Lorentz Force Law tells me what the force is, and therefore what the acceleration is, and that allows me to predict the velocity at a later time. And if I know the velocity, I also know the position at a later time. So imagine you just put this on a computer that then completely traces out the subsequent motion of the particles. Okay? So that is one half of the story. Give the fields, predict the motion of the particles. Right? The law is very simple. How to solve it may be difficult analytically, but in terms of numerics, imagine you do it numerically, that is trivial. Then the other half of the theory is the reverse. If I tell you everything about the charged particles, where they are, how they are moving, in other words, I tell you the charge density and the current density, how do you predict the fields? Okay, so they are sort of two sides of the question. And the second half, the answer to that is given by the Maxwell's equations. Namely, if I tell you rho and J, how do you calculate E and B for all times? All right? And again, writing down the equation is not difficult. You've all learned this in your EM course. Solving it in simple cases, you also know. In more complicated cases, again, it's just a matter of mathematics. You just solve some partial differential equations, and mathematicians have proved, existence, uniqueness, and if necessary, you can just put it on a computer. It's more difficult in that case, but still, it's reduced to numerics. In general relativity, the situation is exactly the same. All right, there are two sides to this equation, to this problem. The first problem, analogous to the Lorentz Force Law, is the following. If I tell you about the fields, now in this case, the field is specified by the metric of space-time. In other words, if I tell you what the metric of space-time is, tell me the motion of the particles. All right? Now, just to remind you, what is the metric of space-time? Space-time is a manifold. On it, there are coordinates, which I call x mu. It's just a grid. The metric just tells me how to compute distances from the coordinates. So it is just the formula that distance squared is given by g mu nu. That is the generalization of the Pythagoras theorem. G mu nu is called a metric. It tells you how to compute distance from coordinates. And the metric tells you the nature of space-time. Is what we call the field. So the first question is, if I tell you g mu nu, suppose you know everything about g mu nu, how do you determine the motion of the particles? That part of the story is similar, analogous to the Lorentz Force Law. And like the Lorentz Force Law, it's the much simpler part of the theory. All right? You learn Lorentz Force Law probably in high school, whereas you learn Maxwell's equations, I don't know, second year in university or something. So that is one part. The other part is again similar. If I tell you about all the particles, in other words, where the particles are and how they are moving, that in fact tells you the energy momentum density. and the energy momentum flux. All right? And together they form what's called the energy momentum tensor, which is similar to the charge density and the current density. Then the question is, if I give you that, which is the source, you tell me what the field is. And the field means G mu nu. All right? So you calculate G mu nu for me. And that is similar to the Maxwell's equations, although it is much more complicated to solve. Much more complicated in a number of senses. One, we would be solving for G mu nu rather than A mu. A mu is 4 quantities. G mu nu is a symmetric tensor. It is 10 quantities. Okay? So it is really 10 equations for 10 unknowns. 10 coupled partial differential equations for 10 unknowns. Whereas A mu is 4 equations for 4 unknowns. In fact, for A mu, we had the good luck, which we show in this course, that you can actually, by a gauge choice, decouple the 4 equations. Right? It's actually four independent equations, 1 equation for 1 unknown. That's why it's easy to solve. Now it's number 1, 10 rather than 4. Secondly, you can't decouple. Secondly, it is nonlinear. Right? And that's what makes no principal superposition. And that makes life very difficult in terms of solving it. But we won't deal with the solution. I just want to sort of write down the equations rather quickly, right? In this course, just to give you a taste. All right? And of course, the second part, the solution to the second part is what's called the Einstein equations of general relativity. Right? And I just want to very quickly, from the mathematical framework and tools we have developed, to quickly lead you to these 2 things. All right? Normally in a relativity course that would take 1 term, so I'm trying to do it in 1 hour. Because with this framework, it's actually not all that difficult. Necessarily, I will have to skip quite a few things. So the first part, the motion of particles, is actually very easy. Now, the motion of the particles, the question you are trying to answer is the following. How is the momentum of a particle changing, right? That's the idea of Newton's second law. Newton's second law tells you, Newton's second law normally, it is better to think of it this way, dp dt is equal to something. That gives you the force law, all right? So it tells you what is the change of the momentum vector after a certain time. Okay, so the momentum vector now is this, later is this. So Newton's second law tells you how much the momentum vector has changed after a while. Okay? And if you know that, then you determine the motion. That's the idea of Newton's second law. And of course, the question mark in terms of Newton's second law is the force. It says the momentum is changing because there is a force. That's the whole idea of Newton. Einstein's idea is the following. As far as gravity is concerned, there is actually no force, no such thing as gravity. And in curved space-time, the momentum is actually not changing. Okay? That's all. But you think the particle is not moving uniformly, that's only because space is curved. Space-time is curved. Right? That's the philosophy. All right? Now, if you adopt this philosophy, then the generalization of Newton's second law becomes dp equal to 0. If I compare 2 moments in time, so let me draw a picture. So here is some sort of manifold, and the particle moves along this path, along the manifold. So at a certain moment, the momentum is a vector, and a little bit later, momentum is this vector. Okay? So dp means p prime minus p, 2 neighboring points, infinitesimal apart. So Einstein says, now this is not actually the way Einstein derived it, right? Einstein derived it in a more complicated way. I will tell you a little bit later. But in terms of our understanding, it's now easier to write it down like this, okay? So momentum actually doesn't change, right? So just write it down, dp equal to 0. What is p? Well, any vector can be written in terms of momentum times the basis vectors, sum over mu, right? P mu are the components of the momentum. E mu are the basis vectors at that point. The basis vectors may be changing because space-time is curved. So you just do the derivative, and that is just mathematics for a product. First, P mu could be changing. and then you have E mu. Then also, E mu could be changing, right? As you move from one point to another point, E mu could be changing, and we derived either last time or the lecture before that this is actually given by, so that I have this. We derive this expression. Now, this expression actually by itself doesn't say very much for the following reason. Dx, the left-hand side is first of all a vector, because it's a difference between two vectors. Therefore, it can always be expanded in terms of the basis vectors. So this power, this factor must come in, all right? Must be expanded in terms of the basis vectors. So if it is expanded in terms of the basis vector E rho, there must be coefficients that depend on rho. Secondly, I am moving by a certain amount, dx. So the change of the basis vectors must be proportional to dx. In other words, I must be able to expand this in terms of the components of dx. So there must be a factor proportional to dx. And because there are these factors, I must also sum over nu. And of course, the whole thing is labeled by mu. Okay? So this statement, all it says is that the left-hand side has the following properties. A, it is actually four quantities labeled by the index mu, so the right-hand side must have a mu. Secondly, it is a vector, so it must have components labeled by rho. Third, it must be proportional to the displacement, so it's proportional to dx nu. And just those considerations imply that there is a coefficient that carries three indices, and you just call the coefficients gamma. Right? So that much really requires no knowledge. I mean, this is the obvious definition. What is slightly non-trivial, but we have proved, is that this gamma is actually a connection one form. And we thought about it in the following way, that we should really think about it as a matrix, gamma. There are four matrices, gamma mu, with components, gamma mu, rho mu. Right? And this is conceptually similar to SUN and so on. Right? So if you do this, then you get the second term like this. All right? Now, I just changed some dummy indices because mu and rho are both summed. They are dummy indices. So I can interchange their names. So mu becomes rho, rho becomes mu, mu becomes rho, rho becomes mu. All right? And the reason I want to do this is that I want the E mu to be the same in both terms, and then I can copy it out. All right? So I have this whole thing is equal to 0. It is something times the basis vector in the mu direction. This is identically 0 as a vector. So the bracket is actually the components of this vector, right? It's something times E mu, sum over mu. So if a vector is 0, all the components have to be 0. So I get an equation without the basis vectors, which is simply this bracket is equal to 0. Okay, so from this, I just drop the basis vectors, I get this. Now, this is a vector equation. These are four equations for the components. Okay, four equations because mu is a free index for me to choose, and they are the four directions in space-time. If this is true for its infinitesimal displacement, I can certainly divide by d tau, where d tau is the proper time elapsed from here to here. All right? So this is just dividing. I get this equation. But we also know that the momentum is mass times velocity. This is a generalization of a formula you know from Newtonian physics, P equals mv, but generalized to four directions. So P mu is mass times the change of the coordinate divided by d tau. So if I put this in, and I cancel the factor of m, because m will appear from this p and this p, then I get this equation, that the second derivative x mu plus gamma dx is equal to 0. So that is the equation of motion for a point particle in general relativity. Okay? So how you solve it is a different matter. It is a formula that tells you what? That tells you the acceleration. Try to move the second, well, move the two terms to two sides. Then one way to think about it is it gives you a law that says acceleration equal to something. And the answer depends on the velocity, right? Acceleration is determined by the velocity. Now, that gives you a second order differential equation that in principle you can solve once given initial conditions, right? In your Newtonian physics, you know that if I have a force law that tells me the acceleration is a function of position and velocity. So if you have something like this, acceleration is some function of position and velocity. Any law like this, you can solve if I give you the initial position and the initial velocity, right? Think of it as doing it iteratively. If I know the present velocity and the present position, let me just write down a formula. Yeah. That means the position at a later time is equal to the present position plus the present velocity times delta t, right? And the velocity at a later time is the present velocity plus the acceleration times delta t, but the acceleration is given by this formula. Okay? So think of doing this in a computer program. So once you have a law that tells you what the acceleration is, and you just keep two numbers, x and v, and you can then calculate x and v at a later time, at a later time, at a later time. Okay? I think in the modern point of view, and this is the approach I try to teach you in year one for those of you who are in my first year courses, all the fancy business of solving differential equations, conceptually you can set aside and just think of it in terms of solving the corresponding difference equations for small delta t. And you know, it becomes conceptually quite straightforward. And in practice, very often that's actually what you do nowadays with such good computers. So in exactly the same way, if I move the two terms to the two sides, this is a law that tells you the acceleration, because it's a second derivative, in terms of something which involves only things up to the first derivative, which therefore is similar to this, except there are four equations, but I think you can generalize how to construct a numerical algorithm for taking it forward, right? So if I give you gamma, then you know the second term, and in principle, you can just solve this numerical equation and find out where the particle is. Okay? Now, remember something. I gave you a formula which I did not prove, that in the case of Riemann geometry, gamma can be computed from G, from the metric. Right? Gamma roughly goes like the inverse G times the derivative of G. Okay? A number of terms of this type. So in principle, if I give you G mu nu, the metric, you do this calculation to obtain gamma. You stick it in this equation. That gives you the second term. Think of it as a force law that is velocity dependent, and therefore stick it in this equation of motion, and you find what happens to the particle. Right, so that is the conceptual thing. And you know, the three classical tests of general relativity are all examples of this equation. Now, the three classical tests are what? Now there are more tests, but classical sort of, you know, soon after the time of Einstein. One is the gravitational redshift of a photon. If I send a photon upstairs, the wavelength increases. Okay? Now, why is it an example of this? Because the wavelength is related to the magnitude of the momentum, de Broglie. And so if this law tells you, for that purpose, it's perhaps easier to go back a few lines and not think about x, but think about the momentum. So this law tells you, which is essentially the same, how the momentum is changing, right? So if I use this law, I can calculate how the momentum is changing as the photon climbs upstairs. Then I can calculate how the wavelength has changed when it goes upstairs. All right? That's a Pound-Repka experiment that tells you, how much the wavelength changes. You can solve. It's a direct consequence of this equation for that reason. That's number one. Second is the bending of light. Oh, by the way, just some numbers. The Pound-Repka experiment was a photon that climbs about 10 meters, right? Done in, I think, early 1960s. And the change in the wavelength was 1 part in 10 to the 15. Okay, very small. Okay? The much more difficult question is how do you measure 1 part in 10 to the 15, not how you solve this equation. That's trivial. The second classical test is a photon passing near, say, a star. Then, just like a bullet passing near a source of gravity will bend. The trajectory will bend. So the trajectory of a photon will bend. So that's called bending of light. So what happens is, so say this is the sun, here is a star. If I exaggerate, it goes like this. So if I observe here, I would think that the star is here. Okay? So the apparent position of the star is changed by a certain angle. All right? So that is another classical test. And how do we think about this? This is the change of the momentum of a photon in terms of its direction. The photon momentum was originally like this. Now it is like this. Okay? So the photon momentum has changed direction. So again, it is given by this law. So you can use this law, you can calculate. And again, just to give you a sense of the magnitude, this is about 1.7 seconds of arc, if we are talking about the sun. Very small. Again, I emphasize it comes directly from this equation. The third classical test is motion of planets. According to Kepler, these are closed ellipses. Closed meaning that the point closest to the sun, which is called the perihelion, right? So say, let me exaggerate. Well, draw it. Here is the sun, and here's the motion of the planet. So it's an ellipse, and this is the closest point, called the perihelion. Closed orbit means that every time it retraces the orbit, and P always stays at that point. But in fact, P advances. So a while later, this ellipse moves to that point. And that's called the advance of perihelion, most noticeable for the inner planets. Let me tell you the magnitude first. The effect in general relativity due to this effect is about 40 seconds of arc per century for Mercury. 40 seconds of arcs per 100 years for Mercury, very small. And it is, of course, the answer would be 0 according to Newton. Okay? This is something you should be able to derive when you learn classical mechanics, right? That inverse square law leads to closed Kepler orbits. Closed meaning a certain number is 0, namely this number. Einstein gives a correction. And how does this follow from here? Well, this is just the equation of motion for a planet. So if I solve this set of, actually 4 equations now, all right? For a planet, which I regard as a point particle, so I just solve this equation, where gamma is obtained from the g mu nu that describes a point mass at the origin, the sun as a point mass. Now, I'm not going to derive these here. I just want to give you a sense that all these 3 classical tests are consequences of this single sheet of equations. Okay, for the first 2, typically we use the third equation. For the last one, typically we use the bottom equation, but they are basically the same. right? Because for a photon, you actually won't write P equals to mass times velocity. You just deal directly with the momentum. And in my relativity course, I have, as most of you here know, gone through all three cases and done the derivation. In these three cases, it is possible to obtain the answer analytically. Because they are basically weak fields, all right? So you can do some perturbative techniques. You can actually get an analytic answer. Whereas in general, of course, you have to do it numerically. Okay? So that's just to give you a sense that this actually captures a lot of interesting physics. The rest is just applications of this formula. And here to emphasize that the key figure in this whole idea is gamma, okay, which is the connection one form. And the connection one form is, of course, a key concept in this whole course. It tells you how one vector space connects to the next vector space. And vector spaces are private. Any questions up to this point? I will say a couple more things about this law. Okay, then I go on. One important property of general relativity, which is conceptually how it all started, is the principle of equivalence. Namely, that inertial mass is equal to gravitational mass. Now, how do the two concepts appear? Normally, in Newtonian physics, we say mass times acceleration is equal to the force, and this we call the inertial mass, right? And let's say it is due to the sun, then the force would be equal to, never mind, the signs will be equal to this, right? And this I call the gravitational mass. The gravitational mass tells you how strong the force is. The inertial mass always multiplies the acceleration and tells you how reluctant is the particle to accelerate. Principle of equivalence says that these two are the same. I can cancel. As a result, the acceleration is the same for every particle at the same point, right? If I place two particles at the same point, namely same r, they would have the same acceleration. So mathematically, it's the equality of the two m's. Physically, it's the equality of acceleration. And of course, the simplest idea is Galileo's experiment from the Leaning Tower of Pisa. Throws a big stone, a little stone, they fall down at the same time. Same acceleration. Now, although Galileo's experiment does not give you a whole lot of precision, but conceptually, that's the idea. Of course, now you can have clever ways to measure it much more accurately, but conceptually, the acceleration is the same for everyone. Mathematically, it's because the two m's are the same. Now, if I come to this formula, you see how this appears. See, this is like the ma term, right? This is a, acceleration. This is like the force term. So let me try to write this the other way. D squared x mu d tau squared is actually minus gamma. I won't write the indices. Okay? So this is acceleration equal to force. That is how I will think about it. And if you want to restore things, this is the inertial mass and this is the gravitational mass. Okay? So the fact that the mass actually cancels from here automatically guarantees the principle of equivalence. And the reason why it all cancels is because all the m came from this same m. And because, you see, if you go back, all you are saying is that the momentum does not change. And every m comes from this momentum. All the m's comes from P equals mv. Nothing else. So of course it is the same m. So principle of equivalence is guaranteed by this formalism because you don't postulate a separate force. See, once you postulate a separate force, like this one, you can always ask, why do I have to have the same mg? I could easily imagine a theory where mg is not equal to mi if you postulate a force. But in this geometric formulation in terms of Riemann geometry, there is no force. It's only that the momentum does not change. There is no force. There is only one way that m appears, namely in the definition of momentum. So there is one and only one m, and that's why they cancel. That's why principal equivalence. Right? So this metric picture guarantees principal equivalence. So that is one concept. Second concept is I want to compare this law with what you know in electromagnetism. In electromagnetism, what you have is mass times acceleration is equal to charge times F mu nu times velocity. Again, I will not write indices, all right? F mu nu is just the electric field and magnetic field. So the first comparison is that the charge and the gravitational mass are sort of analogous, because that tells you the strength of the coupling to the external field. Okay? That is sort of trivial. But the more important point is that in the Lorentz Force Law, you have 1 power of the velocity. 1 power of the velocity, let me write down the case where particles are not moving quickly. You know the velocity, dx mu, d tau, for small velocity is equal to this. Okay? The time component is just 1 because x0 is just t, which is approximately the same as tau. So the time component is 1, and the spatial components is the ordinary velocity. So this one term, when you multiply out, gives you the electric field, electric effect, which is velocity independent. The next 3 components gives you the effect of the magnetic field, which contains 1 power of V cross B. Okay? I won't work out details. So if you work this out, this actually gives you E plus V cross B. The point I want to emphasize is only 1 power of V maximum. Well, 0 or 1 power. Here you have the 4 velocity coming in twice. Okay? So the force now also has velocity-dependent parts, but up to 2 powers of the velocity. So if you want to write something like the Lorentz Force Law for gravity, there is 1 term which is independent of velocity, 1 term proportional to the first power of the velocity, 1 term proportional to the second power of the velocity. Right? So in that sense, the Lorentz Force Law equivalent would be more complicated. Okay? That is because in this picture, gamma is the analog of F, and gamma carries 3 indices rather than 2 indices. So one term you could employ is to call the terms proportional to velocity as, quote, magnetic effects. You see, just as a standing charge gives rise to electricity, a moving charge gives rise to effects which we call magnetism. Magnetic effects carry powers of velocity. So a standing mass produces an effect which is like electricity. In fact, that is just Newton's inverse square law, analogous to Coulomb inverse square law for electricity. But a moving mass produces an effect which is, quote, magnetic. In other words, a gravitational effect that is velocity dependent. All right? And that part is a part that is missed by Newton. This is one of the important corrections to the Newtonian theory, that there are forces proportional to velocity and velocity squared. Okay? So in numeric terms, of course, you know it must be V over C and V over C squared. And this factor applies in magnetism as well, in EM. Of course, there's one point of conceptual difference. In electricity and magnetism was discovered experimentally first, well before the theory developed. In the gravitational case, the so-called magnetic terms were derived theoretically first and then confirmed experimentally, because certain things, you look at it, actually depends on this term. The reason for this, I won't go into mathematics. It's actually very simple. Now, whenever you have V over C, and typically it would be V over C squared, in most experimental situations, they are very small. If they are very small, normally it would be very difficult to discover experimentally. Except that in electricity, there are many situations, because they are both positive and negative charges, the electric effect cancels exactly. So the coefficient, so you think that there are terms proportional to 1, to this, to this. So if there is some symmetry, let's just say just this and this. This is the electric force, this is the magnetic effect. The electric effect cancels completely because of charge neutrality. And so although this term, this factor is small, you can detect it. All right? It's just like 1 plus, say, 10 to the minus 16. If you have the 1, then you can't see the 10 to the minus 16 unless you do very, very accurate experiments. But if you don't have the 1, the 10 to the minus 16 may still stand out. And think about it. That's what happens even in your high school experiments. I'm sure you have done this experiment or seen this demonstration. You have 2 wires carrying currents, right? And they attract each other. Right? That's Ampere's law. Now, in these, say, take one wire. The wire as a whole is neutral. The ions are positive. The electrons are negative. Each of them gives rise to a huge electric force. But because they are exactly equal numbers, the whole wire is neutral and the electric effect cancels. So the wire, because it's neutral, has no electric effect, but there is a net current, so there is a current effect. Right? And the fact that it's V over C squared is because there's V over C here, V over C here in the 2 wires. So this is actually a very easy effect to observe by Ampere, and that was how magnetism was first discovered. But in gravity, although Newtonian 1 over r squared is very similar to Coulomb 1 over r squared, you never have positive and negative signs. It's always attractive. So the leading term never cancels. And these so-called magnetic effects are always small corrections, well, are usually small corrections. And that's why they are difficult to detect. Right? Now, except when you talk about the bending of light. In that case, you are talking about a particle that is moving at V over C equal to 1. This is not a small effect in that case. If you look at the bending of light and try to use Newtonian theory, you are actually wrong by a factor of 2. So relativistic correction is actually a 100% correction because V over C is 1. Okay? The way to do Newtonian theory is the following. Just apply Newton's law to a bullet traveling at velocity v and calculate the bending angle. After the calculation, set v equal to c. That's the Newtonian answer. Okay? And that is wrong by a factor of 2. Okay? So that is another set of comments about this law, just so that you have a feeling how it is actually very analogous to electromagnetism. But to come back to a question I posed to you, you see in the EM case, this is the curvature tensor, right? The field tensor is the curvature tensor. But this is the connection. So in this respect, they are not parallel. Okay? If they were parallel, you would expect on the right-hand side in this equation of motion somehow should be the curvature tensor rather than a connection one form. So the naive attempt to unite the two gets into an obstacle here. Okay? So the unification is still not finished. There is no completely confirmed theory. I'm just saying this is a naive approach that you might think about. It doesn't work. There is a difference. Third remark, if you go back to Einstein's original derivation, the way he proved it was not to say dp equal to 0. This is one way of stating the law of motion. He says that the action is this. Up to, well, there could be a minus sign depending on the metric that you use. He says that is the action, and he says the variation of this is equal to 0. Okay, so on a curved surface, namely space-time, you choose the shortest path, as it were, geodesic. That's the geodesic equation. Okay. Now, you may find it strange. How can you have something like this inside a square root? Well, the way you do it is to you use some path parameter and do this, because it's under square root. So this is a normal sort of integral that you can do. Showing that this leads to the same equation of motion takes a little bit of algebra and is, in computational terms, more complicated. Okay? But conceptually, it's also simple. It takes the sort of extreme path in space-time. And it turns out it gives the same equation. But, of course, this way of looking at it does not naturally lead to the idea of connections. And the fact that this happens because the basis vectors are changing. Now, in this whole discussion, if you do it like this, it's completely in terms of components. You never mention basis vectors. All right? So that is about 1/2 of the story, the motion of point particles. Okay? Then the other half is much more difficult, and I will only write this very schematically. And simply in this form. And this is not even quite the right equation. I will tell you the correction later. It says that there is a thing called energy momentum tensor, which is a T mu nu. It's an object with two indices. It is the source of gravity. It's called the energy momentum tensor, analogous to J mu in EM. There is a coupling coefficient, which is 8 pi times the Newtonian constant. And what is on the right-hand side? On the right-hand side is something like the curvature tensor. Remember, the curvature tensor is just this thing. All right? On the left-hand side is almost the curvature tensor. The G mu nu is defined like this. Roughly speaking, minus half the trace. Okay? I think I got the signs right. And G is called the Einstein Tensor. Roughly speaking, think of it as just R. No, I have to be a bit more careful. This is This is actually a matrix, so it has 4 indices. This R actually has contracted these 2 indices. All right. So this is what's called the Riemann curvature tensor. After you contract these 2 indices, this is called the Ricci tensor. And this is called the Einstein tensor. But basically, apart from contracting some indices, it is the curvature. And you have to subtract this out because T mu nu is conserved. And you need to construct something on the left-hand side that is also conserved. Okay? So this is almost right, except on the right-hand side, you actually have to add a cosmological term. I cannot be sure of the sign, but something like this. Okay? This cosmological constant term is actually describes what is now established experimentally, observationally, what's called dark energy. When Einstein first wrote the equation, he thought there was no dark energy. So relativity textbooks until sort of this last decade would mostly be talking about this equation without the lambda. Right? Now we know that we have to add lambda, although lambda is important only on cosmological scales. If you talk about a solar system or even a single galaxy, you can ignore lambda. So that is an equation. Now, this is actually similar to Maxwell's equations because it says roughly curvature is equal to source. Well, differing by one derivative. EM is derivative of curvature is equal to source. Okay? Because it's derivative of the F mu nu is equal to J mu. All right? So looking at this whole equation, you just demand the right tensor structure. That is the equation that you obtain. And how do you derive the factor 8 pi g? You just require that this, when you reduce it to the limit of slow velocities and weak fields, must give back Newton's answer. Newton's answer tells you how much density or mass density causes how much gravitational potential. Okay? So by just taking the limiting case, you determine the coefficient to be 8 pi g. And this is what? This is a set of 10 equations, because mu nu can each be chosen from 0, 1, 2, 3, but symmetrically. So it's like a symmetric 4x4 matrix. So there are 10 independent entries. 10 equations for 10 unknowns. What are the 10 unknowns? They are little g mu nu. Right? Again, a 4x4 symmetric matrix. So 10 equations for 10 unknowns, coupled, nonlinear, second order. Why second order? Because the Christoffel symbol involves one derivative of the metric, and the curvature tensor involves yet another derivative. Okay? So in mathematical terms, this is a coupled set of 10 nonlinear second-order differential equations. And in cases that are not singular, not too bad, it's easy to prove that solution exists and are unique and so on. Difficult to solve, but numerically it is, in principle, not difficult. Okay? So much of the business of general relativity goes into solving these equations and analyzing what happens. Just as in classical gravity, you learn in first year, you write down Newton's law, and then you discover how planets move. Okay? So now it's roughly similar. Right? So, and you see, the point I want to emphasize in this course is not so much how to solve these equations and so on, that you can learn separately. I just want to emphasize that the key mathematical ingredients that enter the theory of general relativity are, again, number one, the connection one form. Secondly, the commutator between two covariant derivatives, namely the curvature. And these two central ideas, which we also discussed at length in the case of EM, all right, really, in terms of mathematical construct, tie things together between gravity and EM. Okay? Now, in terms, in high school, you already thought about, I'm sure you were already struck by the similarity between gravity and EM. Newton 1 over r squared, Coulomb 1 over r squared. But that analogy is actually very superficial. To further pursue the analogy is really based on all this mathematical apparatus and all these concepts, which are all related to the themes in this course of private vector spaces related to the possibility of making transformations on the vector space. Okay? So I think that concludes the lectures. And I can pause here, first of all, to see whether there are questions, and if not, whether I should try to do a problem that may not have time to go through in detail in the exercise class. But let me just pause for questions.
In general relativities, the mass doesn't change when it moves.
Yeah. Doesn't. No. Even in special relativity, don't say that the mass changes. All right? No, let me go back to special relativity. You have formulas such as this, that the momentum is given by mv over a square root, right? And there is a temptation to call this thing, say, the relativistic mass, and then to say this is equal to mv, right? That's what you mean by, so this depends on the velocity, okay? That's what you have in mind, right? don't do that. Now, first of all, you don't have to do that, right? You just write the complicated formula. Now, what's wrong with writing the relativistic mass? Because behind it is the implicit assumption that once you do that, a lot of formulas in Newtonian physics become correct if you just substitute that mass. Okay? Now, that is true for some formulas. In an elementary course, the first few formulas you come across are okay in that sense. But not every formula. If you go further along in your study of special relativity, there are other formulas that cannot be simply made right by making that substitution. So if you insist on making that, writing the symbol, you can mislead yourself into thinking that's every formula can be made right this way. All right? For example, if I have a charged particle moving very rapidly, and I have a force that is perpendicular to the direction of motion, and I want to calculate its acceleration. Now, it turns out it is correct to do this. In other words, essentially the inertia increases by one factor of the square root, which is just gamma. 1 over the square root is gamma. Right? If it's moving very rapidly, it is not very willing to be bent, the motion, by one factor gamma. But if it's moving very rapidly and I apply a force in the parallel direction, it turns out it's worse. The inertia does not change by one factor of gamma. It changes by 3 factors of gamma. The reason is actually heuristically easy to understand. Because if it's along the direction of motion and it's getting close to c, no matter how hard you push, it cannot exceed c, right? Because it's running up against an absolute upper limit. So of course it won't accelerate. It's very reluctant to accelerate because of that ultimate limit. And that's why there are 3 powers of gamma. Okay? So if you try to use the relativistic mass and put it into F equals ma, you will be wrong for this problem. Worse yet, in a case where the force and the velocity make an angle that is neither 0 degrees nor 90 degrees, there is no simple formula that will make it right. So you just have to go back to the fundamental formulas with all these factors. Okay? So in proper discussions, you never use the concept of a relativistic mass that is velocity dependent. Now, if there are no questions, I want to perhaps spend half an hour. I think I won't need a filming for the rest. It's just an exercise. Perhaps you can take an early break.